Okay. In fitting hearing aids to individuals, researchers wanted to examine whether there was a difference between hearing words in silence or in the presence of background noise. Two equally difficult word lists are randomly presented to each person, one list in silence and the other with white noise, in a random order for each person. This means that some people get silence, then noise, other people get noise, then silence. Are the hearing aids equally effective in silence or with background noise? First, conduct a t-test assuming that these are independent samples. Then conduct a t-test assuming that these are paired samples. Which test is more powerful, the independent samples t-test or paired samples t-test? And we'll need to figure out what it means by more powerful. Okay, so I need some scratch paper here because that problem was so long. I'm just going to divide this space in half, right? And this top part I'm going to use for assuming independent samples. They aren't actually independent samples, but I want you to see the difference between doing them as independent samples and doing them as paired samples. Doing this hypothesis testing as paired samples. So step one, the hypothesis, the null hypothesis, is that if I get these samples and they're independent, I get the mean here, get the mean here, this difference of means on average is going to be 0. So the mu sub x bar minus y bar is going to equal 0. The alternative hypothesis is that the mu sub x bar minus y bar does not equal 0. Here I'm going to put alpha equals 0.05, two-tailed. And I'm going to draw myself an S dot. And just so that you know, it's the differences of means. I don't know if that helps, but okay. So here we know that this is going to be 0, and we probably should find out the standard error. So the standard error of this difference of means is going to be the square root of the variance of x bar plus the variance of y bar, right? And I'm going to write this out to be s sub x squared over n sub x plus s sub y squared over n sub y. So the variance of x, not x bar, but the variance of x over n and the variance of y over n. Okay. And we'll probably need to find the degrees of freedom, right? And that's going to be n sub x minus 1 plus n sub y minus 1. And finally, we'll probably need to know the critical t, but I'll put that up here. Critical t, what is it? So let's look at this data. Go to example 3, click on example 3. Let's take a look at this data. And let's assume independent samples. Here we're going to assume that this silence is just one group of scores and this background noise is another group of scores, and they're not paired. But they are actually paired. This belongs to subject 1, these two belong to subject 3, this belongs to subject 5, right? And here's the list order. It's A, B. So they get list A first, then list B. And here's the noise order. They get it silent first, then noisy. This guy gets noisy first, then silent, right? And so all these orders are randomly assigned. And the list the list orders are randomly assigned, and the noise orders are randomly assigned as well. But for this exercise, we're going to assume we don't know any of this stuff, right? We're going to assume this is gone, and that this is just a bunch of scores from one group of subjects that listen to a list of words in silence, and another group of subjects that listen to a list of words in background noise. Okay, so when we do the independent samples t-test, and we start with step 3, we know we need to find the standard error, which is going to be the square root of the variance of of x, variance of x, divided by n of x. Oops. I forgot a parenthesis at the front. Plus the variance of y over n sub y, right? And all that added together, find the square root. So we need to find the variance of x. We need to find n sub x. We also need to find the variance of y and n sub y before we can find standard error. So variance is pretty easy. So we'll just call silence x. And the count of this, I assume, is 24. Yep. And the count for y is going to be the same. But what is the variance of y? The variance of y is slightly different, right? And so in order to find this guy, the standard error, then we're going to put in square root of the variance of x divided by 24 plus the variance of y divided by 24. Great. And we get a standard error of 2.26. And since standard error gives it to us in terms of words, it's number of words, right? Number of words accurately heard. All right, we also needed to find the degrees of freedom, right? And in order to find degrees of freedom, we need the degrees of freedom for x plus the degrees of freedom for y, right? So the degrees of freedom for x is just going to be 24 minus 1. And the degrees of freedom for y is also going to be 24 minus 1. So this, the new degrees of freedom, is 23 plus 23, 46. Once we have that, I could just move this down. Once we have that, we could find our critical t. So our critical t, we know that alpha is 0.05. So we're going to put in t inv and put in our two-tailed probability and the degrees of freedom, 46. And we get a critical t of plus or minus 2.01. So our critical t is plus or minus 2.01. And I'll just leave this stuff on there, on the Excel file. Given all this, now let's deal with the sample. When we find the sample t, what we're doing is finding the difference in means, right? And then find the difference between that difference and our expected difference, 0, and divide all of that by standard error to find how many standard errors away we are. So here I'll put step 4, sample t. I'll move this up so you can see it. Okay, so in order to find sample t, we need to find x bar minus y bar minus mu, and all of this, divided by standard error. Thankfully, we have a bunch of those things available to us quite easily. We have x bar, we could get y bar, we could get standard error, we already have it in fact. So let's find x bar. The average number of words heard accurately in silence, and that's about 33 words. And the average number of words heard correctly with background noise, and that is 29 words. Now, is that difference of about, 3 or 4 words, 4 words-ish, is that difference big enough to be statistically different? So we would take this minus this, And we know mu equals 0, so I'm just going to ignore that, over standard error, which we found up here. And that would give us 1.75. And we see, 1.75, that's not more extreme than plus or minus 2.01, right? And so 1.75, we would actually say do not reject, right? We should find the p-value too, right? P-value. And so this p-value should be greater than 0.05. So we would put in t dist, put in our sample t, our degrees of freedom, which is 46, and we want a two-tailed. And we get 0.09, right? 0.09 is greater than 0.05, right? So step 5, fail to reject. Ta-da! We failed to reject. We're not rejecting that sucker. Okay. Now that we have all that, we want to know, is it more powerful? Is it more sensitive, right? Can we detect a statistical difference better if we use paired samples? Well, let's go see. So let's start. So here we would say p equals something like 0.09, I think it was, 0.08, 0.09. And so 5 is fail to reject. It's not outside of our rejection zone. It's inside. It's inside our fail to reject zone. Okay,